So today what we're going to look at is another way of determining limits. So we're evaluating limits and we're going to use derivatives to do that. And this is called L'Hopital's rule. So I want to first start out by just showing you where it comes from, okay? So here's a graph. The blue is the graph of f, and also the red is the graph of what we're going to call g of x, okay? And so there's something important to notice here, okay? That right here at A, all right, f of A is equal to 0. So f of A equals 0. And also g of A is equal to 0. So both these things are true. So this is a condition that must be met in order to use this thing called L'Hopital's rule. Some people call it La Hospital, right? And that's actually it's L'Hopital is actually French for hospital. Okay. Okay. So over here in this diagram, what I've done is I've zoomed in on like a box, like I've done zoom box with a graphing calculator, and that's what this is right here. Okay. So it's just a zoomed in feature of this. Okay. So one thing that I want to point out is this point right here. Okay, is a comma of f of a. All right, and it's also a comma g of a. All right, because they share that point. So this is also a comma g of a. All right. Now what we're going to do is we're going to go x units to the right of this. Okay. And we're going to go, we're going to do this one first. So I'm going to put a point right here. And this point right here is going to have an x. Okay. So that means that's some x value. And so the point right here would be x comma f of x. All right. Now, a couple things that we need to point out. This distance right here, because let me explain. We just created a slope triangle, right? So this horizontal distance right here would be x minus a. And this vertical distance would be f of x minus f of a. And I want it to be like that right now, okay? So you might say, well, Mr. Mitchell, that's just f of x minus 0. And you'd be right, okay? But for right now, I want to write f of x minus f of a. Okay. We're going to do the very similar thing right here, okay? And we're going to come straight down and right here. And this point right here, I'm going to label as x comma g of x. And again, I'm going to draw in this slope triangle, okay? So something like this. So this horizontal piece right here, this horizontal leg would be x minus a. And this vertical piece right here would be g of x minus g of a. And it would come out to be negative because g of x is lower than g of a. All right. Okay, so now we're ready to describe some things, okay? And I'm going to start out by saying, okay, so what is f prime of a over, that's the derivative of f at a, so over g prime of a. And we're going to go back and we're going to use the definition of a derivative at a point. And one of the definitions for derivative is you can take the limit as x approaches a of f of x minus f of a over x minus a. Okay, so that's the derivative. That's the definition of derivative of f prime of a. It's this definition right here. And I'm going to zoom in a little bit so you can see it a little bit clearer. All right, and then this one we can do the same thing, but instead of having f's, it's going to be g. Okay, so the definition of the derivative of g at a is the limit as x approaches a of g of x minus g of a over x minus a. I'm going to extend this main fraction bar right there. Okay, so what do we know about this f of a and g of a? Well, f of a is 0 and g of a is, so this one's 0 and this one's 0, which leads us to write the limit as x approaches a of f of x over x minus a over, okay, because that's just going to be 0. And then this one's also going to be 0, right? So this denominator becomes the limit as x approaches a of g of x over x minus a. So we have a complex fraction, right? So what can we do to clear out the denominator? Well, we can take this and we can multiply by x minus a over x minus a. That's a version of 1. So when I multiply this by 1, nothing's going to change. Okay, it's going to look differently. Okay, because when I multiply this, I can multiply this times f of x over x minus a, and my x minus a's are going to cancel. So now what I'm left with is the limit as x approaches a of f of x over, and then x minus a's here cancel too. So I'm left with the limit as x approaches a of g of x. And we're taking the limit as x approaches a of this numerator and the limit as x approaches a of this denominator, and limit as x approaches a, they're the same, right? So we can write this as one limit, and that limit becomes the limit as x approaches a of f of x over g of x. Okay, so what this says is, what this is saying is that if you take the limit as x approaches a, now this is equal, right? So these are the same thing. So this is a way of calculating limits, all right? Is if we take the limit as x approaches a of f of x over g of x, that's going to equal f prime of a over g prime of a. Now, there is one thing that must be said, and that is this whole thing was based on, this whole argument was based on this f of a and g of a being 0, because that allowed this to become f of x and this one to become g of x. So for this to be true, these two both have to be 0, okay? So we have to show, and this is going to be an important step in all this, we always are going to have to show that the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x has to equal 0. All right, so if we try to plug it in, we're going to get 0 over 0, which allows us, if we get 0 over 0, that's going to allow us to take the derivative of each one and find the limit that way. So this is something we could have done way back in the first unit, because what we were getting is 0 over 0. Now, I was showing you an algebraic way of manipulating that function so that we could find the lit. Now there's a calculus way of doing it, right? And it requires derivatives. Okay. All right. So really, let me slide this up a little bit. Here's L'Hopital's rule, the first form. Okay. We're make this supposition. We're supposing that f of a and g of a is equal to 0. If it's not, this doesn't work. So if f of a is equal to 3 and g of a is equal to 0, this doesn't work. You can't use it, okay? So that's really important, that these have to equal 0, okay? And then you take the derivative and just plug a in, okay? And then the derivative down here can't be 0, because then you have something that's undefined. Okay, so let's do a problem with this. So for this problem, okay, estimate the limit graphically. You could put this in your graphing calculator and look and see, okay, graphically, what is, as x approaches 1, what is this quotient getting closer and closer to, okay? And so you can look at that and go, oh, it's going to come out to be this, all right? But we're going to do L'Hopital's rule. So I'm going to save some time just by going straight to L'Hopital's rule on this. Okay, so let's take a look and see what happens, okay? So what happens if we try to do the direct substitution, right? We try to put it in here, and the cube root of 1, well, the cube root of 1 is 1, minus 1 would be 0. So the top is going to become 0, and then the bottom is 1 minus 1. Oh, that's also going to be 0. So we get 0 over 0. We get this intermediate form, okay? Now, you can't just do that in your head. You have to write this out, okay? And this is required of you, that you have to write 2 limit statements. Every time you use L'Hopital's rule, you have to show that the limit is going to take on like this 0 over 0. And there's going to be some other forms that I'm going to show you in just a little bit too, okay? So if we have to show this, that the limit as x approaches 1 of the cube root of x minus 1 is equal to, and we just did it mentally, okay, but it's equal to 0, right? So I'm fine if you just say, oh, that's going to equal 0, okay, but you have to make this statement. And you also have to make this statement, the limit as x approaches 1 of x minus 1, well, that's also going to be 0. So you don't want to do a direct substitution, okay, because this is, you can't equal, something can't equal 0 over 0. And that's why you can't write, oh, this is equal to 0 over 0, okay? You have to write these two limit statements, okay? Now, this is x to the 1/3, so I'm going to go right to taking the derivative, okay? So we have the limit as x approaches 1 of the cube root of x minus 1 over x minus 1. So this is equivalent to the limit as x approaches 1 of, and what we're basically going to do is we're going to take the derivative of the top over the derivative of the bottom, okay? So this is x to the 1/3, so the top becomes 1/3 x to the, and we subtract 1 from 1/3 and we get negative 2/3, okay? And then minus 0, which we won't have to write, over, and then the derivative of x would just be 1. Okay, so this becomes the limit as x approaches 1 of 1/3 times 1 over x to the 2/3 power. When we put 1 in here, right, we're going to do that substitution. We get 1 over 3 times 1 to the 2/3 power. Well, 1 to the 2/3 power is just 1. So this denominator is just 3. So the answer to this is 1/3. Okay. So that's a way that we can use L'Hopital's rule. Okay. This is really important. You have to make this statement. You can't say any of this other stuff without first stating this. Okay. That's the condition that must be met. All right. Okay, let's look at a little bit stronger form of this. And in actuality, this is what I just did. I just in that first example, I did this, right? I took the derivative and then I found that limit, okay, by plugging the a value in. All right. Now, g of a or f of a and g of a both equal 0. Okay. F and g are differentiable in the open interval containing a, and the denominator here can't be 0. Okay. Now what this is saying is that sometimes you're going to need to do this. Okay, so the limit as x approaches the of a of fx over g of x. If f of a and g of a both equal 0, then you're going to have to take the derivative. Well, what happens if you get 0 over 0 again? Well, you're going to take the derivative of f prime of x and the derivative of g prime of x. So if it doesn't work the first time, you have to keep taking the derivative. Okay, so this would equal, okay, so then this would equal the limit as x approaches a of f double prime of x over g double prime of x, which is equal to, okay, the limit as x approaches a of f triple prime of x over, you just keep taking the derivative of the top and the derivative of the bottom until something happens, okay? All right. Okay, and I should say this, you can only go to this if the limit as x approaches a of f prime of x equals 0, and the limit as x approaches a of g prime of x equals 0. So if we have that, we can make this statement, okay? So let me show you in this next example how this can play out, okay? All right, so what we want to show, okay, so what if we do angle pi over 2? So theta is pi over 2, okay? So if we put pi over 2 into the sine function, right, that means our y is going to be the same as the radius. So it's going to be 1 over 1, which is 1. So this is going to be 1 minus 1, which is 0. What happens if I put pi over 2 in here? Well, 2 times pi over 2, that'd be pi. Cosine of pi is -1. So this would be 1 plus -1. All right. So it does help us see, this is where it helps us to be able to do evaluate trig functions mentally in our head. Okay. And like picture, oh, that's going to be on the positive y-axis. Oh, that's going to be on the negative x-axis. Okay. And what is the ratio of sine and cosine? Okay. So this one's going to be 0 and this one's going to be 0. Okay. So we're going to say the limit as theta approaches pi over 2. You guys, I'm going to switch to a smaller pen. So hold on a second. Okay, so I got 0.7 instead of 1.0. All right. So we have the limit of 1. The limit is theta approaches pi over 2 of 1 minus sine of theta. And oh no, it looks like my pen's going out. All right. So this is equal to 0. Okay, because sine of pi over 2, remember sine of pi over 2 is right here, right? And the y and the r are both the same, so it'll be 1 over 1, which is 1, right? Okay. Let me try to find another pen. Okay, and we also have to make this statement: the limit as theta approaches pi over 2 of the 1 plus cosine of 2 theta. Okay, so if we put pi over 2 in here, this becomes pi, right? And pi is right here. Okay, and cosine would be x over r, right? So our x would be -1 and our r would be 1 right here. So that'd be -1, but we're taking 1 plus -1. That's also going to be 0. Okay, so we've met the conditions to use L'Hopital's, right? The limit of the numerator becomes 0 and the limit of the denominator becomes 0 as theta approaches pi over 2. Okay, so that means the limit as theta approaches pi over 2 of 1 minus sine theta over 1 plus cosine of 2 theta. We can determine this by taking the derivative of this and the derivative of this and finding the limit as theta approaches pi over 2 of that. So this is equal to the limit as theta approaches pi over 2. The derivative of 1 is going to be 0, and the derivative of sine is cosine. So this top becomes negative cosine of theta over, and this is going to be 0, and the derivative of cosine is negative sine. So this is going to be negative sine of 2 theta times the derivative of the inside function, so that'd be times 2. And so this becomes the limit as theta approaches pi over 2 of negative cosine of theta over -2 sine of 2 theta. So let's take a look. What happens when we plug pi over 2 in here? Cosine of pi over 2. Well, cosine, your x would be 0, right? So this is going to be 0. Okay. And what happens when I put pi over 2 in here? Well, 2 times pi over 2 is going to be pi. Sine of pi over 2. Well, sine is y over r. Well, over here, our y is going to be 0. So that when we multiply that by -2, that's going to be 0. We're going to have 0 over 0 again, right? So that means we have to write this again, right? So the limit as, and I'm switching colors to show you, I'm going to switch this again. The limit as theta approaches pi over 2 of negative cosine of theta, that's equal to 0. And the limit as theta approaches pi over 2 of -2 sine of 2 theta is again equal to 0. So we have the situation where we have 0 over 0. So we take the derivative again, right? So that means this is equal to the limit as theta approaches pi over 2. Okay, so the derivative of cosine is negative sine. So we have negative of negative sine. Okay, so negative of negative sine of theta over -2. Derivative of sine is cosine. So cosine of 2 theta times the derivative of the inside, which is 2. Okay, so this becomes the limit as theta approaches pi over 2 of sine of theta over, and this becomes -4 cosine of 2 theta. So what happens when we approach pi over 2 here? Okay, so pi over 2 is right here. Sine is y over r. Our y and our r are both the same here, right? So this is going to be 1. Okay, so we're no longer getting 0 here, right? So this is going to equal 1 over -4 cosine of 2 times theta. Well, theta is pi over 2. So this right here, this angle right here becomes pi. Cosine of pi, well, that'd be over here, right? And our x is -1 and our r is 1. So this is going to be -1 times -4. So, or -4 times -1, right? And this becomes 1/4. So this limit is 1/4. So this is something, back when we first did limits, you weren't even able to do this, right? Because you didn't know derivatives, right? But then you also couldn't algebraically get rid of the discontinuity that we had, that hole. Whenever you get 0 over 0, you have a hole, right? So that's what we have. We have a hole, and we're figuring out what that limit is because we're not actually able to do the direct substitution. And this is just the way we can find the limit without using algebra. Okay. All right. So that's example number 2. Let's do a couple more. So for this next problem, we're taking the limit as x approaches 0 from the right. So we're looking at one side of the limits. Okay. And we're also, for part A, we're going to look at it as x approaches 0 from the right. This one, we're going to look at it as the limit as x approaches 0 from the left. Okay. So to the right of 0, okay, if when you do one-side limits, you can try to do just the direct substitution. And if we try to put 0 in here for sine, right, sine of 0, okay, angle 0 would be on the positive x-axis, and your y is 0 there. So this is going to be 0. Trying to plug 0 in here, that's going to be 0. Okay, but once again, you have to make these two statements. The limit as x approaches 0 from the right of sine of x, it's going to equal 0. And the limit as x approaches 0 from the right of x squared, that's also equal to 0. So now what we can do is we can apply L'Hopital's rule, right? So this is going to be equal to the limit as x approaches 0 from the right, and then the derivative of sine x is cosine x, and the derivative of x squared would be 2x. Okay, so now we try to do the direct substitution. Cosine of angle 0, okay, so cosine of angle 0 would be +1. And so this becomes the limit as x approaches 0 from the right. Now, we can't plug this one in, right? Because this one's going to become 0, okay? But the top is going to become 1 over 2x. Okay, so what is this equal to, right? So what's happening is this is going to get closer and closer to 0, but this number right here is positive. So when you multiply it by 2, it's going to be positive. So you're taking 1, dividing by a number that's close to 0, but positive. Okay, so what does that mean? That means this is going to go to infinity. So this one's equal to, I'm going to come down here, line up my equals. This is equal to infinity. Okay, so what we know is that the limit as x approaches 0 from the right of sine of x over x squared is equal to infinity. All right, how about this one? Well, it's going to be the same process, but we're approaching 0 from the negative side of 0, right? So all of our x values are going to be negative, okay? But we think of this as the sine of 0, that's going to be 0 again, and 0 squared, that's going to be 0. So we have the situation where we have 0 over 0 again. So we're going to write the limit as x approaches 0 from the left of sine of x, which would be equal to 0, and the limit as x approaches 0 from the left of x squared, that's also going to equal 0. So we have 0 over 0. So this is equivalent to writing the limit as x approaches 0 from the left of derivative of sine x, which is cosine of x, over 2x. Now when we go to plug 0 in, cosine of 0 is once again, this is getting closer and closer to 1. So this becomes the limit as x approaches 0 from the left of 1 over 2x. So this 2x, because x is getting closer and closer to 0, 2x is getting closer and closer to 0, but all of our x values that we're putting in here are going to be negative. So this is close to 0, but negative, which tells you that you're taking 1 and dividing by a negative value here, right? And it's going to be really, really close to 0, which is going to make this really, really big, but negative. So what this tells us is that the limit as x approaches 0 from the left of sine of x over x squared is equal to negative infinity. So one of these is infinity and one of them is negative infinity, okay? So we can use L'Hopital's rule when we get 0 over 0, but we can also use L'Hopital's rule when we get infinity over infinity, okay? So the limit as x approaches pi over 2 of secant x, that's going to come out to be infinity or negative infinity, depending on what side of pi over 2 you're coming from. And then 1 plus tan of pi over 2, that's also going to approach infinity. So let me show you how this is going to work out, okay? So we're going to take the limit as x approaches pi over 2 of secant of x. Well, secant x is 1 over cosine of x. So this would be the limit as x approaches pi over 2 of 1 over cosine of x, okay? And so cosine becomes pi over, is getting closer and closer to being 1 as x approaches, I'm sorry, as x approaches pi over 2, let me draw it, which would be this angle right here, okay? Your cosine is x over r, and your x is getting closer and closer and closer to 0. But you can approach pi over 2 from the right, but you can also approach pi over 2 from the left. Okay, so this is going to wind up being, because this is getting closer and closer to 0, one of them is getting closer and closer to 0 from the right, and one of them is getting closer to 0 from the left. So this is actually coming out to either be positive or negative infinity. Now, the sign of it doesn't matter. It's that we come out with infinity, all right? And then we also have the limit as x approaches pi over 2 of 1 plus tan x. Okay, and 1 plus tan x, okay, as we get closer and closer to pi over 2, this is also going to either go to infinity or negative infinity. Okay, so it helps to know the graph of tan x for this. So this is also going to be plus or minus infinity. All right, which tells us we can use L'Hopital's rule. So we take the derivative of the top and the derivative of the bottom. So this would be equal to the limit as x approaches pi over 2. The derivative of secant x is secant x tangent of x. And the derivative of 1 plus tan x would be secant squared x. So this is the limit as x approaches pi over 2. This secant x here cancels with one of these, and we're left with tan x over secant x. And then what we can do is use trig identities. Tan x becomes sine x over cosine x, and secant x becomes 1 over cosine x. So this becomes the limit as x approaches pi over 2 of sine of x over cosine of x, all over 1 over cosine x, because this is tan x and this is secant x. And then what we can do is clear out this complex fraction by multiplying by cosine of x over cosine of x. And this would give us the limit as x approaches pi over 2. And we have sine x over 1, which would just be sine of x. And now we can actually plug this in, right? So what is sine of pi over 2? We can actually evaluate that. Sine of pi over 2 is, so angle pi over 2 is right here. Y over, so my x is 0, my y is 1, and my r is 1, right? That's what I've been doing the whole time, okay? So y is 1, r is 1, so that'd be 1 over 1. It's 1. Okay, so really this is about, if you get 0 over 0 or positive or negative infinity over a positive or negative infinity. So they don't have to be the same types of infinity. You could have one be positive, one be negative. They could both be negative. They could both be positive. But if you have the situation where you have some type of infinity over some type of another infinity, like we do here, so the plus or minus really doesn't matter. It's that we have infinity over infinity. Then that means we can use L'Hopital's rule. Okay. All right. Let's do a couple more examples. Okay, so what happens as x approaches infinity of ln of x? Okay, so ln of x, we've got to remember what the graph of ln of x looks like. It has a horizontal, or not horizontal, a vertical asymptote, comes up and goes this way. And so as x goes to infinity, this just keeps getting bigger and bigger and bigger. So what we know is that the limit as x approaches infinity of ln of x, as x gets really, really big, ln of x keeps getting bigger and bigger and bigger. So it also goes to infinity. Okay. And then what happens when we take the limit as x approaches infinity of 2 square roots of x? Well, the square root of x just keeps getting bigger and bigger and bigger, right? As x gets bigger. So this is just also going to go to positive infinity. So both of these are going to go to infinity, which means we have infinity over infinity, which means we can use L'Hopital's rule, right? So that means this becomes the limit as x approaches infinity, and the derivative of ln of x is 1 over x. Okay, and the derivative of 2, and remember this is 2x to the 1/2, so that'd be 2 times 1/2 times x to the negative 1/2. That's the derivative of 2 square roots of x, would be this right here. So that means this becomes the limit as x approaches infinity of 1 over x over, and this is 1, and this would be 1 over x to the 1/2. So what we could do to clear both these out is multiply by a version of 1, and it'd be the highest power of x. So in that case, it would be x over x. And so this becomes the limit as x approaches infinity of 1 over x to the 1/2. And so that's the square root of x. So this is getting bigger and bigger and bigger and bigger. This is getting huge. And when you take the number 1 and divide by a really, really big number, you're going to get a number that's really, really close to 0. So that's what this is equal to. It's equal to 0. All right. So what we know from this is that the limit as x approaches infinity of ln of x over 2 square roots of x is equal to 0. Okay. All right, last problem, and it'll be a little bit easier one, okay? Okay, so we're taking the limit as x approaches 0 of 7x minus sine x over x squared plus sine of 3x. Okay, so if we try to do direct substitution, this is going to be 0. Sine of angle 0 would also be 0. So we have 0 minus 0. This top is going to be 0. And when we try to do direct substitution here, this is going to be 0. Sine of, and 3 times 0, this would be 0. So sine of 0 is still 0, okay? So we need to write these two statements. We're going to need to do this every single time. The limit as x approaches 0 of 7x minus sine of x. That's equal to 0. And we also need to show that the limit as x approaches 0 of x squared plus sine of 3x. That's also equal to 0. So we have 0 over 0, right? So that means we can use L'Hopital's rule. We can take the derivative of the top, derivative of the bottom, and just take the limit as x approaches 0 of that. So the limit as x approaches 0 of, and this would be 7 minus, and the derivative of sine x would be cosine of x over, and this would be 2x, and plus, and then derivative of sine is cosine. So this would be cosine of 3x times the derivative of the inside, which would be 3. Okay, so if we try to put this in, this is going to, cosine of 0 is going to be 1. So this is going to give us a number up here. This is going to give us 0 right here. Cosine of, and this angle right here, 3 times 0, that's going to be 0. So cosine of 0 is 1 times 3. So this is going to give you 3. This is going to give you 0, right? So this becomes 7 minus, we're going to be able to just plug everything in, 7 minus cosine of 0 over 2 times 0 plus cosine of 0, because 3 times 0 is 0, times 3. So this would be 1, because cosine of 0 is 1. This would be 7 minus 1 over 0 plus, and this would be 1 times 3, so 3. So 0 plus 3. So this becomes 6 over 3, and so that's 2. So from this, we know that the limit as x approaches 0 of 7x minus sine x over x squared plus sine of 3x must equal 2. Okay, guys, that's it for today.